Hello everyone, so today we are going to look at evaluating a linear regression model. Evaluating a linear regression model. Okay, and we'll break everything down step by step just like we always do. So we're not going to shy away from the math, and if need be, we'll go deep into it, but we'll make sure we really understand it. Okay, so why do we need to evaluate a model? So imagine you are building a robot. I don't know how to draw a robot. I'm not going to embarrass myself. Okay, imagine you're building a robot that predicts house prices based on square footage, right? But if the robot keeps on giving terrible predictions, no one will trust it. That's why we need a way to check how well our model is performing, and we call this model evaluation. And then for model evaluation, if you are following the series, you might already be familiar with some of the concepts we will look at. If not, then we will just walk through everything again in this video, so don't worry. Let's start by understanding error, okay? Very fundamental but very important. What is error? In a perfect world, our predictions, which is our y hat, would match the real values exactly, right? If the robot predicts that, the robot being our model, linear regression model, predicts that the house will sell for 200,000, and in real world it does sell for 200,000, then that's a perfect match. But in reality, there will always be some error, which is the difference between our predicted value and the actual value right here. Now, what do we do with these errors? We can't just add them up, because some will be positive and some will be negative, which would cancel each other out, right? So instead, we take the square of each error before averaging them, and this gives us mean squared error. Mean squared error, okay? So mean squared error is the average squared difference between our predicted values and actual values. What are the key terms? Average squared difference between predicted and actual values. So mathematically, your mean squared error is 1 by m, which is number of training examples or number of data points and number of rows, by sum for each and every row or your data points, yi minus y hat. Okay, where y hat is your predicted value and then yi is your actual value. So why do we square the errors? Because one, we want to make sure that all errors contribute positively, and two, because we want to penalize larger errors more than the smaller errors. Okay, now we will look at something that's very similar, which will also help us in evaluating our model, and it's the mean absolute error. What is mean absolute error? Very similar. The only difference here we see is the term absolute, right? So your MAE is going to be 1 by m, I, 1, m, and then here, instead of squaring, I'm taking the absolute value. Okay, so what does this do? This gives us an easier way to interpret measure of error, since it tells us on average how much we are off in the same units as our predictions. And one thing that it's not doing is penalizing bigger errors more than the smaller errors, right? It's just showing what it is. So it's using absolute instead of a squared value. So that's the difference between mean squared error and mean absolute error. Now this might be a newer concept for some of you and might be a familiar concept. The third concept we're going to look at is your R squared, which is coefficient of determination, which tells us how our model fits the data. So imagine we are trying to predict the house price, and then when we are trying to predict, what do we have? We have two choices. One, we can use our regression model to predict the house price, right? Two, we can just guess the average price for every house, which is pretty dumb if you think about it. I'm not really taking into consideration different factors that might play. I'm just saying, oh, what's the average price for a house in this location? And then, hey, yeah, it should be the same for any other house. So if our model is no better than just guessing the average, then it's pretty much useless, right? That's exactly what R squared tells us. It compares our model's error to the error we would get if we just use the mean of y. Okay, so let's look at the math. Okay, your R squared is going to be your 1 minus sum of residual by your total sum of squares, or also written as your 1 minus your residual sum of square by total sum of square. Okay, so you might see it appear either way. Now I'm going to break these terms down. Okay, so what is your total sum of squares? Total sum of squares. Total, so we're doing the summation, total sum of squares minus, so how much do actual values vary from the mean? Okay, how much do actual values vary from the mean is what your total sum of squares looks at. And then you have your residual sum of squares, which looks at how much do actual values vary from the predicted values. Okay, residual sum of squares. So since it's residual, your residual term is going to be this, the actual value minus your predicted value, and then we're just going to square this, and then you have the sum. So total sum of squares, residual sum of squares. Okay, and then your R squared then is just going to be your residual sum of square by total sum of square. Okay, so if R square is 1, then it's perfect prediction. If R square is 0, then our model is no better than guessing the mean, right? Pretty useless. And then R square is less than 0, then that's really sad, because that means our model is worse than just guessing. Just guessing the mean, it's worse than that. So yeah, that's where you know your model is really bad, not doing much. But as you get closer to that, then like you're getting closer to perfect prediction. Okay, now I quickly want to touch on bias variance trade-off. And I might not go a lot into this. I can do a separate video on this, but okay, bias variance trade-off. Okay, now why do some models perform well on training data, but then you apply it on your testing data or new data and then it's terrible? It really just all comes down to finding the right balance between bias and variance. Okay, so if there's high bias, then that means what's happening is underfitting. So model is too simple. Example, you're predicting your house prices with just number of doors. It's too simple, it's underfitting. And it really just fails to capture patterns, leading to high training and testing error. So when there's high bias, usually you see high training and testing errors, right? So that's your high bias. And then your high variance, when the model is too complex. In a way, it's trying to just memorize every house's price instead of really just trying to figure out a trend. Okay, so it leads to overfitting. So it really just works really perfectly on your training data, but then when you give it new data, then it fails miserably. So our goal really is just to have a model that captures patterns, but then at the same time it generalizes well, right? We don't want it to memorize, but we don't want it to be so simple that it just fails to capture the important patterns. So this right here, you want to get into a sweet spot. Okay, and Okay, let me quickly mention this. What if I told you, like, adding more data doesn't always sort of improve your model, okay? A learning curve helps us visualize how error changes as we add more data. So if the training error is high, and then testing error is high, and high bias, underfitting. If the training error is low and then the test error is high, then high variance, overfitting. And if training and test error sort of are converging, then usually that's a good generalization. So if you see your test error sort of decreasing but still far from a training error, then at that point is when having more data might help, but not always, okay? And yeah, so we covered our mean squared error, mean absolute error, you know what your R square is. We looked at bias variance trade-off. If you want me, let me know, and I can do a deeper dive on this so that it's clear, because I think it's a very important concept. And then we briefly talked about learning curves, where checking if adding more data might help. So yeah, just go ahead, try to evaluate your model, and I am going to see you on the next video. Take care.